In this episode, we are going to discuss the boiling process and the boiling point. Boiling is a special form of evaporation. In this process, the conversion from liquid state to the gas particles, vapor, occurs within the body of the liquid. In the last episode, when we talk about evaporation, we made it clear that evaporation only occurs on the surface of the liquid. But how come here evaporation occurs within the body of the liquid? Well, it only occurs when vapor pressure of the liquid is the same as the external pressure exerted on top of the liquid. Well, I think we all can understand what this statement is talking about. But why? What's going on? Why when the external pressure equals the vapor pressure, vapor will be formed within the body of a liquid? Well, this is how we're going to understand this. We're going to do an experiment, a boiling experiment to boil some water. During the process, we will examine what's going on in each step and try to understand what's going on in the boiling process. So now we're ready to do an experiment. We're going to boil some water. Since boiling is a special form of evaporation, let's review some of the conclusions we learned from the last episode. Here are a couple of conclusions we had from our last evaporation experiment. Inside flask C, the pressure exerted by the vapor in flask C is called the vapor pressure, and the vapor pressure is the maximum pressure the vapor can get for a liquid at a given temperature. Another conclusion we had was the vapor pressure increases with the increase of temperature. Higher temperature, higher vapor pressure. All right, keep this in mind. Let's go back to do our experiment to boil some water. All right, we're ready to boil some water now. But before that, let's remind ourselves again. This is the conclusion we have from the evaporation experiment. The vapor pressure of a liquid is the maximum pressure the vapor can reach at a given temperature. All right, let's do the setup of boiling water experiment. I'm going to pull out a rain stand. All right, I'm going to secure the rain here. On the rain, I'm going to put a wire gauze, where you can put something on it and heat it. Then I'm going to place on top of the gauze a beaker. To the beaker, we're going to add some water. We're going to use water as the liquid to do the boiling experiment. Now I'm going to put in a few pieces of boiling chips. Anytime you boil water or boil any liquid, you add some boiling chips or boiling stones. Now I'm going to place my Bunsen burner at the bottom. Well, before we turn on our Bunsen burner, start heating the water to boil it, let's look at these water liquids again. We know there are so many water particles, molecules are here in the liquid body, and they are attracted together by the attractive force. Right now at room temperature, we are not heating yet. At room temperature, some of the molecules on the surface can get evaporated. And our conclusion from last time is that molecules here within the body of a liquid, they cannot evaporate. Well, why not? Let's assume they can. If the molecules on the surface, you get the chance, the opportunity to evaporate, to go to gas and become free, to have total freedom. Why can't we here, some molecules here within the body of water, why can't we evaporate? Well, let's assume they can. Let's assume some of the molecules within the body of the liquid, let's assume they can evaporate. And if they do, what will happen? If a lot of molecules here within the body, they all evaporate at the same time, what will happen? They will create a bubble here, vapor bubble. Does that make sense to you? All right, so let's assume they can do that. Once the bubble is generated, what is inside this bubble? Tons of water vapor molecules. Now let me ask you a question now. Inside this bubble, what is the maximum pressure? What is the maximum pressure can this bubble have? Well, the maximum pressure will be the vapor pressure of water under room temperature. Remember, we haven't started heating yet, so right now the temperature room temperature. If that bubble forms, the maximum pressure inside that bubble will be the vapor pressure of water. How do you know that? We just did the experiment in the last episode, the evaporation experiment. All right. However, at room temperature, the water's vapor pressure is way less. The vapor pressure is less than 1 atm, 1 atmospheric pressure, which is the pressure here exerted on the surface by the atmosphere. If that pressure, let's assume it's 1 atm right now, if that pressure is greater than the vapor pressure of the bubble, can that bubble form? Can a balloon just expand itself without being blown in a lot of gases so that it can resist the atmospheric pressure? So that bubble cannot form because the vapor pressure is lower than the external pressure. It will be squeezed right back. There's no way it can form that bubble. Does that make sense to you? And that is why at room temperature, evaporation only occurs on the surface of the liquid. Inside the liquid, there's no bubble. So, all right. Now let's start the Bunsen burner. Let's start the Bunsen burner, start heating. What happens? Temperature is going to increase. What was this other conclusion we just reviewed from our last evaporation experiment? Higher temperature, higher vapor pressure. So when the temperature is increased, when you're heating the water, the vapor pressure of water is increased. Higher temperature, higher vapor pressure, higher temperature, higher vapor pressure, until at one point, the vapor pressure of water is the same as 1 atm. When that happens, bubble can form within the body of the liquid. Now, the inside the bubble, the pressure is the same as the external pressure. Now, that atmospheric pressure cannot squeeze the bubble. The balloon can be blown up now. Does that make sense to you? Yes. So at a certain temperature, when temperature is high enough, then the vapor pressure of water is the same as the external pressure. Now they can form the bubble within the body of the liquid. And once the bubble forms, it will flow to the top of the liquid. And that's what you see in the boiling process. Tons of bubbles form within the body and they all flow on the top. That is boiling. Boiling. That's why boiling happens when the vapor pressure of the liquid is the same as the external pressure. That's why they can form the bubble within the body. So starting from now on, next time when you're at home to boil some water, watching what's going on with the water, you'll understand exactly what's going on. All right, that's the end of our boiling experiment. Let's move on. A boiling point, the temperature at which vapor pressure of a liquid becomes equal to the external pressure. Well, the temperature at which boiling occurs, that's the boiling point. So boiling is a process. Boiling point is the temperature at which boiling occurs. If the external pressure is 1 atm, 760 millimeter mercury, if that is the case, the boiling point, the temperature, is called the normal boiling point. Like the normal boiling point of water is 100 degrees Celsius. That means at 100 degrees Celsius, the water's vapor pressure is 1 atm, is 760 millimeter mercury, is the same as the standard atmospheric pressure. Remember another conclusion from the evaporation experiment on the relationship between the vapor pressure and the attractive force. Remember that? What is it? Well, this is the experiment. In C, that's the vapor pressure. Another conclusion is that liquids that have strong attractive force between molecules will have lower vapor pressure. Or makes sense. For vapors to evaporate, it has to overcome the attractive force between the molecules in the liquid to go to the gas. Okay, so if there's attractive force among the liquid between the molecules in the liquid, if the attractive force is strong, then there will be less liquid get evaporated. It's hard to evaporate, so the vapor pressure will be lower. Make sense? In the next episode, we will learn what are the attractive forces. The attractive forces between molecules are called intermolecular forces, and that's our next episode's topic. All right, let's move on. So our last conclusion from the evaporation experiment, another conclusion was lower vapor pressure, stronger attraction between molecules. If a liquid has lower vapor pressure, the attractive forces between its molecules is stronger. Well, lower vapor pressure means if a liquid has a lower vapor pressure, in order to make it boil, in order to make its vapor pressure is the same as the atmospheric pressure, you need a higher temperature. So lower vapor pressure means stronger attractive force between molecules. Stronger attractive force between molecules means higher boiling point. The stronger the attractive forces between molecules, the higher the boiling point. Boiling point also changes with elevation. Atmospheric pressure is lower at a higher elevation. So when atmospheric pressure is lower, when the external pressure is lower, you do not need that high temperature to make the vapor pressure equals the external pressure. So as a result, higher elevation, lower boiling point. So higher elevation, lower boiling points, and here are some boiling points data for different spots on the Earth. Us, we're close to New York City. Water here boils at around 100 degrees Celsius. Look at the top of the Mount Everest, Tibet. Their water boils at 70 degrees Celsius, 30 degrees lower than us. Now let's look at this question. Where does it take longer to boil eggs? Make sure the eggs are fully cooked. Here or at the top of Mount Everest. Okay, at both places, well, some water, eggs in the cold water, we start the heating, temperature rise at the same time at both places. At 70 degrees Celsius, Tibet's water starts to boil. Remember, once water boils, the temperature will stay at the boiling point. So once both places water reaches 70 degrees Celsius, the Tibet water pot will stay at 70 degrees, will start boiling, and temperature will stay at 70 degrees Celsius. As the water temperature is rising, eventually it's going to reach 100 degrees Celsius, and water starts to boil. Temperature will stay at 100 for us. So basically, we are cooking our eggs at 100 degrees Celsius. Tibet people can only cook their eggs at the highest temperature of 70 degrees Celsius. Of course, it takes longer for them to cook the eggs. Our eggs will be fully cooked sooner. Make sense to you? Another question, what is the vapor pressure of water at 100 degrees Celsius? How do you know? Of course, 1 atm, 760 millimeter mercury, because we know 100 degrees Celsius is the normal boiling point of water. The normal boiling point of water is when its vapor pressure equals 1 atm, the atmospheric pressure. So the vapor pressure of water at 100 degrees Celsius is 1 atm because water boils at that temperature. That's it for today. See you next time.